Jai Hind everyone. Today we are going to start with routing algorithms. Before starting routing algorithm, let us discuss what routing is. Routing is just a simple process of sending one packet from source to destination. But which path to follow, which route is required to be followed, that will be considered, that will be described with the help of routing algorithms. So, in simple words, we can say routing algorithms that determines the route. That means which output line an incoming packet should be transmitted on and maintain the routing table. For that, there are few of the desired properties which are required, that is correctness, simplicity, robustness, stability, fairness and optimality. So, now we will be starting with the routing algorithms. First of all, the question arises, what is it that we seek to optimize? What is required to get optimized, right? So, the answer is minimizing mean packet delay. We need to minimize the mean packet delay, maximize total network throughput, and these are the goals which we say that are in conflict. Why it is so? Since operating any queuing system near capacity implies a long queuing delay. That is the reason, right? So, as a compromise, many of the networks attempt to minimize the number of hops a packet must make, because what is the benefit of this? It reduces the number of hops, tends to improve the delay and also reduce the amount of bandwidth consumed, which tends to improve the throughput as well, right? So, that is why it is required. So, next we have the classes of routing algorithms. We are having two classes of routing algorithm. One is static, which is also known as non-adaptive routing. Second is dynamic, which is called as adaptive routing algorithm, right? So, what is a static routing algorithm? The static table is not changed according to the network conditions. As the name is indicating static, that is a static, that is not going to be changed according to the conditions. That means if the current traffic is getting changed, or it is too heavy or too low, and the topologies. In the case of static routing algorithms, the route is computed in advance. We are not allowed to change according to the network conditions, right? Next we have, that is dynamic or adaptive routing algorithms. These change routing decisions to reflect changes in topology and traffic. These differ in the source of information as well as metric used, right? So, as the name suggests, dynamic, it is dynamic in nature. That means it adapts the changes on which depend on the network condition. If the current traffic, if there is a change in the current traffic, if there is a change in a topology. So, these are the algorithms which can adapt the changes dynamically. These are the routing protocols which we use in the respective routing algorithms. We have two classes over here. One is intra-domain, second is inter-domain. Intra-domain routing protocols, here we have two categories, distance vector and link state routing algorithms. And here in inter-domain, we have path vector routing. Then what are the protocols? RIP, which is routing information protocol, is used related to distance vector routing algorithm, and open shortest path first, this protocol is used for the link state routing algorithms. Here for the path vector routing algorithm, we use border gateway protocol, which is also known as BGP. What is the optimality principle? When we say optimum path, optimum route that needs to be optimized, what does it mean? What that optimality principle is? It states that if router J, say any router is there, router J, that is on the optimal path from the router I to router K, right? Then the route from I to J and the route from J to K are also optimal. Fine. Okay. The set of optimal routes from all sources to a given destination from a tree rooted at a destination, and that type of tree is known as sync tree. What is that sync tree? Let me show you with the help of this diagram. We can see over here. A sync tree for the router B metric is the number of hops, right? So, now we will be starting with the routing algorithms. First, that is the shortest path routing. To compute the shortest path from A to D, that means this is our source and this is our destination, right? So, how to do that? Here we will be using Dijkstra's algorithm. Now we say what we need to do? We need to opt for the shortest path, right? Suppose source is A and destination is D, right? Fine. If we see node A, from the node A we have two paths, A to B and A to G. We see the distance, that is 2, A to B that is 2 and A to G that is 6, right? So, which one is shortest? We see 2 is shortest as compared to 6. Okay, fine. A to B, we say, okay, the distance was 2 and from where it has come, we are considering that is A. Okay, next, from B to C or B to E, which one is shorter? We see B to E, that is 2, right? So, 2 plus 2, it becomes 4 over here, right? Now, again we need to check from E to F and E to G. E to F, that is 2, E to G, it takes only 1, right? So, if it takes only 1, the distance from E to G, it becomes 5. Now, again we have two routes, the further we have G to H, and what is the distance from G to H? That is 4. Okay. If we take G to H, it becomes 10, right? But if we opt for the another one from E to F, which is 2, it becomes 4 plus 2, that is 6, right? Now, from F to C and F to H, if we consider, we see that is 3 over here and it is 2 over here. So, we will be considering F to H, right? 6 plus 2, that becomes 8, right? So, that will be the shortest path from the source A to the destination D. So, that's how this algorithm works. We simply need to compute the shortest path from A to D, from source to destination. The next we have flooding. Flooding, as the name is indicating, it floods and transmits a copy of each packet it receives on every one of its transmission links. Whatever number of transmission links are there, it will send on every transmission link, right? So, but what is the advantage in this case? It is robust, quite simple, broadcasting and discovery. These are the advantages of flooding. But still, we are having some disadvantages as well. It uses too much resources, because every time it transmits a copy of each packet it receives on every one of its transmission links, right? So, how to curb the following? How to curb the flooding? We have hop count, timestamp and sequence number, which helps us to curb the flooding. A more practical variation is selective flooding. That means instead of copying each packet on each and every transmission link, we will be sending on few of the links. In this algorithm, the routers do not send every incoming packet out on every line, only on those lines that are going approximately in the right direction, right? So, that is what known as selective flooding. Another algorithm, routing algorithm, that is the distance vector routing algorithm, and it is very important routing algorithm as far as your university examinations are concerned and your competitive exams are concerned and so on. Okay, so we see what distance vector routing algorithm is doing and how it is working. It operates by having each router by maintaining a table, that is a vector, right, where it will be having the best known distance to each destination, which line to use to get there, right. These tables are updated by exchanging information with the neighbors. What is the how many neighbors are there, what is the distance of each and every neighbor and how it will be going on, right. So, say destination B, the cost is 10 and the link via which route, right. Say destination C, the cost we say 12 via B, for example, right. How these tables are being maintained? Let me show you over here. Fine. Suppose these are the participating routers over here, and here we have included the cost and the values of each and every distance, right. So, how it is working? Assume the delay is used as a metric. Once every t milliseconds, each router sends to each neighbor a list of its estimate delays to each destination. It also receives a similar list from each neighbor, so that the complete table could be maintained, right. Let one table has come from the router X to router Y, right. We say xi is some of the value, that is the delay from x to I, and y knows the delay from y to x is m, right. It will now calculate the delay from y to I as xi plus m, fine. We see in this table. We have prepared few of the tables over here, that is for the from the vector j to a to I to h and to k, right. This is a new estimated delay from j, this table shows, right. So, we say from j to a, if we calculate, what is the delay? Delay is 8. Right. From the vector j to I with respect to j I. Okay. So, with respect to j, for the I we need to check, that is what, 10, right. So, here we can see this is the value 10. For the vector j h, okay, for h we need to consider with respect to h, we see here that is 12. For k, okay, we need to check it out for the k with respect to j, that is 6, right. So, this is what new routing table for j, and these are the vectors received from j's 4 neighbors. A, what are the neighbors of j? That is A, I, right, and then H and then K. Fine. So that is how we have identified. Right. Okay. Next we have a count to infinity problem. What this count to infinity problem is and how it is going to affect the routing algorithm we will be discussing. Simply we say there are 4 routers A, B, C, D and E, right. Initially we say A is down. When A is down, that means if A is down, B, C, D, E, that means the other neighbors, they know that there is no link to communicate with A, right. Okay. Now we say A is up and this table has been updated. That means from A to B we have a transmission link and the distance is 1. It takes 1 to reach B, right. Okay. B tell fine, I do have a link to A and the distance is 1, right. So then C will come to know, okay, if the distance is 1 via B and I am having again one distance apart from A, that means 1 plus 1, it will become 2. It will update its table. Next, it will update, D will update its table. Next, E will update its table. So that's how it will be updated after 1 exchange, 2 exchange, 3 exchange, 4 exchange and so on. A is up. That is a good news for the neighbors, right. So the good news spreads quickly, we say, right. But there is a little bit another problem. What that problem is, suppose initially A is up, but later on A comes down. Excuse me. Now we say the bad news travels slowly. That means this is not known to each and every one of the participating router that A comes down, right. Now say B says I don't have a transmission link with the A, right. I don't have any information whether it is there or not, or like any communication link is not there, right. But C doesn't know that A goes down. C says I do have a link to A via B and it is at a distance, of 2. Then B thought if C is having a transmission link to A via B, okay, fine, that means it is at one distance apart, right. So it will update its value. B takes 2 units or at a distance of 2. So 1 plus 2, that is 3. Now C thinks, okay, this is the value of B. B is at 3 distance apart from A and I take 1. So 3 plus 1, it becomes 4. Now this news spreads again for the A, and A updated its value again 3 plus 2, it becomes 5. C updated its value 3 plus 1, that becomes 4, and similarly D updated its value 4 plus 1, it becomes 5 and so on, right. After one exchange 2, 3, 4, 5, 6 and so on. That means it becomes infinite. That's why this problem is known as count to infinity problem, right. So as a solution, the split horizon hack that was introduced. Many ad hoc solutions to the count to infinity problem have been proposed, and split horizon algorithm works the same way as we have seen in the case of distance vector routing algorithm, except that the distance to X is not reported on the line that packets for X are not sent. Actually, it is reported as infinity. Fine. So that is how it is working. Say initially the information was with the B that A goes down, right. When it has seen that A goes down, it marked it as infinity. I don't have any information regarding the same, right? Okay. When C came to know that there is no link with the B, B has no information, because earlier we have seen C assumed that it is having a link to A via B. But now when C came to know that there is no transmission link or there is no path for A via B, it immediately also updates its value as infinity. Similarly D does, similarly E does, right? That's how we have solved the problem of count to infinity, right? It becomes successful in most of the cases, but still few of the cases are there where still we have count to infinity problem. What is that? Suppose these are the participating routers A, B, C, D, right? When C to D line goes down, A think it has a path to D through B, right? A think it has a path to D via B, and B think it has a path to D through A, right? Here again A and B will count to infinity. That means a split horizon, although it works very well in most of the cases, but few of the cases are still there where it is not working properly. So next we have the link state routing algorithm, right? We have seen few of the advantages and disadvantages in the earlier routing algorithms. Here we see the distance vector routing that was replaced by link state routing algorithms. What is the reason? Here we have two primary reasons caused its demise. That is, number one, since the delay metric was Q length, it did not take line bandwidth into account when choosing the routes. The algorithm often took too long to converge, even with the tricks like split horizon as well, right, as we have seen in the last slide. For these few reasons, it was replaced by an entirely new algorithm which is known as link state routing. So now we are going to discuss link state routing, and here are 5 main steps of this algorithm. The idea behind link state routing is quite simple and can be stated as 5 parts, and each router must. These are the 5 steps. Number 1, firstly, discover its neighbors and learn their network addresses. First, it has to identify who all are my neighbors. I need to confirm the network addresses of these neighbors. Measure the delay or cost to each of its neighbors. What is the delay? What is the cost to reach that neighbor? It has to identify. Each and every router has to identify, right? Then construct a packet telling all it has just learned. Now construct a packet which will be informing every other neighbor that it has just learned that you are its neighbor, what is the cost, what is the delay. Now send this packet to all other routers and compute the shortest path to every other router, right? What is the difference in distance routing algorithm and the link state routing algorithm? We see with the link state routing algorithms, routers share only the identity of their neighbor, but they flood this information through the entire network, right? In case of distance vector algorithm that adopt an opposite approach. What that opposite approach is? Routers periodically share information with the entire network, but only with their neighbors. No, they are not going to flood this information throughout the entire network, right? What it is going to do with their neighbors. Fine. So now we will be discussing each and every step one by one. Number one, learning about the neighbors. When a router is booted, its first task is to learn who its neighbors are. First, it needs to identify who all are the neighbors. How it does? It sends a hello packet to each and every point-to-point line. Fine. And then every receiving router that is on the another end, that has to reply by telling who it is, right? When two or more routers are connected by a LAN, the situation is slightly more complicated. Why it is so? How we will cope up this complication? So one way to model the LAN is to consider it as a node itself. Then we can cope up with the situation, right? How we'll do that? Like this one, right? This entire LAN is considered as a artificial node, right? One way to model this LAN is to consider it as a node itself. That's what we are doing over here, right? Second step, it has to measure the line cost. In the first step, it has sent a hello packet to each and every participating router. Now it is sending a echo packet to each and every participating router. The link state routing algorithm requires each router to know or at least have a reasonable estimate of the delay to each of its neighbors. The most direct way to determine this delay is to send a special echo packet, right, over the line that the other side is required to send back immediately, right? So now this distance will be measured, right? By measuring the round trip time and dividing it by 2, the sending router can get a reasonable estimate of the delay. That is how it is measuring the line cost. An interesting issue is whether or not to take the load into account when measuring the delay. To factor the load in, the round trip timer must be started when a echo packet is queued. That means when it is at the front of the queue, front end of the queue, right? To ignore the load, the timer should be started when the echo packet reaches the front of the queue, right? Excuse me. Third step, which includes building link state packets. Every router must be having information of its neighbors. So firstly, I take the example of router A. Who all are the neighbors of A? That is B and E, right? B and E. The distance from A to B is 4. The distance from A to E is 5. Similarly, for B, the neighbors are A, C and F. A, C and F, and respective distance 4, 2 and 6, right? We see over here. Third one, that is C. The neighbors of C, which are B, E and D. B, D and E and the respective distances. Similarly for D, E, F. Fine. Building the link state packets, it's quite easy. What is the hard part? To determine when to build them. That is a big challenge, right? Number one, either periodically or when some significant event occurs, right? Such as a line or the neighbor going down, number one scenario, or coming back up, right? So these are two possibilities. Fine. The fourth step we have, that is distributing the link state packets, which is trickiest part of the algorithm. to distribute the link state packets reliably. As the packets are distributed and installed, the routers getting the first ones will change their route. Consequently, the different routers may be using different versions of the topology, which can lead to inconsistencies, which can lead to the loops, which can lead to the unreachable machines, or any other kind of problems may arise, right. So, what is the solution? And how to handle this? The fundamental idea is to use flooding to distribute the link state packets, right. But how to keep a check while flooding? To keep the flood in check, each packet contains a sequence number that is incremented for each new packet sent. Routers keep track of all the pairs they see, that is the source router plus sequence. When a new link state packet comes in, it is checked against the list of packets which has already been sent, right. If it is new, forward on all lines except the one it is arrived on. If it is duplicate or the older one, then simply that needs to be discarded, right. To guard against errors on the router lines, all link state packets are acknowledged, and that will also be included in the table. Fine. Packet buffer for the router B, here we have taken the sources, say F, A, F, E, C, D, accordingly a sequence number and the age of the packet, plus the sending flag and the acknowledged flags with respect to A, C and F, right. That means its neighbors. We are preparing the table for router B. So, what are the neighbors? That is A, F and C, right. So, A, C, F for this sending flags and the acknowledgement flags. The last one, that is the computing new routes, right. Once the router has accumulated a full set of link state packets, it can construct the entire subnet graph because every link is represented. Now, Dijkstra's algorithm can be run locally to construct the shortest path to all possible destinations, as we have seen in the beginning of the lecture, right. So, the next category of the routing protocols, as we have seen in the earlier slides, that is interdomain routing. One was intradomain, second is interdomain routing. Interdomain routing is the protocol in which the routing algorithm works both within and between domains, within and between domains. Domains must be connected in some way for host inside one domain to exchange data with host in another domain. This connection within domain is governed by interdomain routing protocols. And for interdomain routing protocols, we are having a protocol that is BGP. We use that. This is often done using the border gateway protocol, which is BGP, right. It is used in path vector routing, using which interdomain routing is performed. Now, what the path vector routing is? In path vector routing, the routing depends on the analysis of the path from the nodes in the current domain to the node in the other domain. But obvious, when we are talking about interdomain, so we will be talking about one domain to the another domain, right, and not on the distance between the nodes, right. So, that is about interdomain routing algorithm. So, in this particular lecture, we have discussed about the intradomain and interdomain routing, and we have seen the categories of routing algorithms as static and dynamic routing algorithms, and that is what we have discussed. And here these are the references from where I have included the contents in my slides. Thank you.